Thank you. Well, it's great to be here today. I cannot do what was just done there with all the different labs at OSU doing work in my area because I'm still fairly new here and I guess I didn't put in that work. So that was really amazing. I'm mostly going to talk about my role in the water impacts of climate change research and point to the fact that there are a lot of different people presenting today in posters or presentations that you're going to hear more about water and pay attention to that because I'm not going to give you all of that background here. But thank you for inviting me to speak today on the ways in which climate change impacts water. I want to acknowledge that the research I'm presenting today is really a joint collaborative endeavor by me and colleagues at Ohio State as well as colleagues across the nation. So Ohio State University investigators that you'll hear more about later today and some just now have a breadth of climate change and water resource research from polar dynamics, coasts and oceans, land surface hydrology, groundwater, and food and water security. The water cycle, for those of you who don't know, hydrology is the study of water, and the water cycle or hydrologic cycle is how water moves through the planet, including the atmosphere. So the precipitation falls as rain or snow, warmer temperatures drive evaporation or the return of water to the atmosphere, and in between are the paths that water travels through Earth's surface. Every aspect of the water cycle is affected by a changing climate. We're dependent on the water cycle in a lot of different ways. We need water to drink, support ecosystems, grow crops, and we need that water to be clean for most of those activities. We also need to be protected from hazards such as flooding, so there's Superstorm Sandy, New York City, other extreme events, droughts. Hydrology changes driven by climate change have the potential to seriously impact human welfare on the planet. I'll just call out a couple more things here. We have accelerated soil erosion and algae blooms in Lake Erie. These are closer to my area of research. If you have more extreme events, you can get greater soil erosion than what we would have expected, and farmers may not be managing for that expectation because it hasn't occurred yet. And the algae blooms in Lake Erie are somewhat climate change driven in that we need warm conditions in the lake to grow the algae, as well as what's coming in from the watershed and the nutrients. These topics are very important to stakeholders globally, but in our particular research, we look at mostly speaking with stakeholders in the Great Lakes region or generally in the Midwest. These stakeholders want to poise themselves for a future climate. The hard thing is giving them good predictions of what that future climate will look like, not just from the climate side, but from the hydrologic side. How is the climate change going to impact hydrology? It's been really difficult to tell them definitive answers on what that's going to look like. Especially how will this climate change affect agricultural and urban areas. This is deep uncertainty, an area of deep uncertainty, and we're working to try to make predictions under this deep uncertainty by linking models, linking climate models with hydrology models. I'll talk about watershed models, which are a type of hydrology model today. So it's common for us to use computer models to try to look at all of this, and basically in that water cycle figure, I split it up into approximately where the different models could reside. We're going to have models simulating the atmosphere and the climate, models simulating the hydrology, models simulating the ocean. I don't do anything in the ocean, but and those boxes are not exactly where they should be. Some models span some multiple areas there. So it's fairly common practice for people to take outputs from one model and put them into the next model and then just see what those, propagate those predictions through models. It can be, that is done across campus. We have a number of people doing that. That's a very common practice to be looking at with our research. The idea of ensemble modeling is also very strong in the climate model field. So we have ensemble, multiple climate models come together to help us understand what do we really expect in a future climate and what range of expectation do we have. We're not relying on just one model to make an estimate. So you represent the Earth in many different ways. You forecast perhaps many different pathways of future development and CO2 emissions, and you look at the weight of evidence of what that future climate might be. You get a range of possible changes and a median. Ensemble modeling is not as common in watershed modeling or hydrology modeling, and so I'm going to be talking a little bit more about some of the research we're doing in this area today in a moment. This is an example of, using an ensemble, this isn't exactly an example of using ensemble of climate model predictions in a watershed model. It's actually just looking at sensitivity of a watershed model to climate changes in climate. And so what I wanted to represent here in this figure is some of our work where we're looking at just changing future temperature by up to 5 degrees Celsius. How much does that affect river flow in one of our watersheds? And we see that the watershed model is extremely sensitive in its springtime river discharges. It's extremely sensitive to changes in temperature. And you can imagine, and I could have shown you, change in precipitation, there's at least as much sensitivity there. So hydrology will respond to climate. But again, using an ensemble of climate models is the way that we usually do this. So some of the sometimes the range can be very large in looking at the predictions coming through climate models, through watershed models. And the variation can be due to very good reasons, like the climate models have different, maybe we're looking at different pathways, or they have different assumptions built in, and we don't know our future. But there can also be areas of research where we might be able to improve prediction. And one of the things I'd like to point out is that the Great Lakes region is not very well, I'm not a climatologist, but the Great Lakes region isn't terribly well captured in global climate models. In fact, many of them don't even have pixels of lakes at all in the Great Lakes region. And we know that the climate here is very impacted by our lakes. So thinking about, are there ways, as a hydrologist, I'd like to see climate modelers think about ways to work on making the climate models better for the hydrology models running the results coming out of those in Great Lakes watersheds. Okay, so one of the issues that, one of the other issues I've been looking at, which is related, is the issue of bias in climate models. So climate models don't predict perfectly in the present day time period in a particular area, and some of them predict worse than others. So can we either reduce that bias or use that bias in some way to select climate models or fix that problem? So I'm sorry, I didn't realize I was on this slide, but this is the slide about bias. So generally people bias correct, which means you just sort of force the results to look more like they did in the historical time period, and then you apply that to the future as well. But there are some concerns that bias correction isn't going to totally solve the problem. But why is there bias in the first place? And can we reduce that? And then if you do bias correct, are you changing something fundamentally about what that model was telling you? So it may be necessary, though, to get a reasonable prediction of hydrology. So another example from same watershed that I'm showing you everything from here in the Great Lakes region, but in Northwest Ohio, looking at the precipitation and temperature dynamics from 5 climate models that we chose in a study based on having decent precipitation performance in the historical time period, we found that the precipitation maybe had up to a 20% wet bias in these models, which wasn't so bad compared to the whole set that we looked at. But what was really problematic was a 4 degrees Celsius cold bias that some of these models had. That's a lot of a cold bias. And it was rather humorous when we were working on this big linking project to link climate, or link the climate data through the watershed, and we went all the way to a lake ecosystem model. And this was just really funny. We couldn't grow algae in our lake because it was too cold. And if only that was our reality here. So we actually were unable to complete that aspect of the project because of the issue of bias from the climate model. So you can see that error propagates through the models, and this can be problematic. All right, the last main research thing that I want to show you from our work relates back to ensembling of both climate models and watershed models. So the context of this work is, again, Northwest Ohio, or the Maumee River watershed draining to Lake Erie. We have agricultural nutrient runoff, nitrogen and phosphorus, which results in eutrophication in the lake, the algae blooms, the harmful algae, the hypoxia. So what we were doing in this study is trying to predict what a future climate meant for hydrology by looking at not only 6 climate models, but 5 hydrology models. And so this is, and I'm going to call out that Haley Kuyava will be presenting more on this particular aspect of the research at the poster session. My master's student, she's great, you should go and see her poster. So some of the findings that we had from the study were quite expected, and some less so. So the expected findings First, the choice of the climate model of those 6, so which climate model you chose to look at determined what your river discharge looked like. So if you chose a climate model that said the future would be wetter, then you would have more river discharge. A drier future meant less river discharge. That makes a lot of sense. So this little graphic here, you can see if there's a large purple bar, that means that most of the variation in our results was explained by the climate model choice, whereas the red would be from the hydrology or watershed model choice. The second finding followed from that is that nitrogen loading generally followed the discharge relationship too. So nitrogen, which is one of our 2 nutrients that we're focused on here, sort of followed with the discharge. And most of the literature there's not a whole lot of literature on ensembling both climate and hydrology models, and most of it stops at discharge, says the climate model is important for discharge, and we think that clearly nutrients should follow suit. That makes sense. The nutrients travel with the flow. The surprising finding, and by the way, nitrogen in the watershed we're looking at is mostly traveling through subsurface drainage, so one main drainage path in this watershed. The surprising finding was with phosphorus, which is arguably more important for Lake Erie and the Great Lakes and freshwater systems for the eutrophication. So phosphorus loading did not follow river discharge. So what you see here in these 2 figures, you have total phosphorus on the left, dissolved phosphorus on the right. The dissolved has been blamed for much of the algae bloom and problem. And what we can see is that most of the variation explained in our results was from the choice of hydrology model. In other words, the hydrology models were not agreeing about whether phosphorus load should be going up or down in a future, under a given climate model. And so the main reason that I think this is true is that there are 2 main pathways in this watershed for phosphorus to travel: surface runoff, subsurface tile drainage. And they're both really important in this watershed. And so those 2 main pathways and how much flow is going through those paths in the models, it gets a little more complicated. But I think the important point here is that phosphorus loading, nutrient loading, does not always follow the discharge, and there are very few studies looking at this. Also, the choice of the watershed model was really important for nutrients. And so if you stop at saying, oh, the climate model drove everything with discharge, and you don't look at multiple watershed models, you may be missing a big part of the picture for nutrients. Where do we go from here in my sort of small area compared to the breadth of what we're talking about today? But I could see several ways that we can move forward here. So recognizing the importance of warming on future hydrology. The other thing that people often do is they say precipitation is changing, and then they think that's what affects hydrology. Well, the warming is also really important in hydrology. I didn't really show that to you today, but believe me, we're finding that if a warmer future, even if it's a little wetter, might produce less discharge and less nutrient load. Don't expect nutrients to always follow the water. Nutrient transport can be a little bit more complicated than that, and you should be simulating that in your models. Using an ensemble of watershed models may help your prediction, especially for nutrients if you're looking at climate change. The impact of bias correction on hydrology is something we're looking at, we're concerned about, and we're trying to figure out the best thing to do about that. And we really would love if you could just eliminate bias from your models, right? I know that won't happen. Selecting climate models, this may be a little controversial, but if your climate models have a lot of bias, can we down select to a smaller number based on having less bias? So that's something we're looking at, saying these models perform better in this region, so we're going to focus on them over the others in the ensemble, and improving the climate models to reduce the bias. And then ultimately, some researchers are doing this. We're not with our particular watershed model, but coupling climate and hydrology models so that there's one model with all of this going on is certainly a way to move forward into the future. I want to end by just recognizing again, there's a lot of research going on in a breadth of hydrology research on campus. And I appreciate being asked to speak on a small part of that breadth. And I just want to remind you that the changes to our global climate are already threatening our water resources. And it's really important that we can understand these impacts, but also be able to forecast them for our stakeholders so that farmers, residents, governments, societies are able to adapt to this changing climate. Thank you very much.